Hi, I'm Eric, and I'm going to present our work on redeeming intrinsic rewards via constrained optimization. To start, consider the following maze. We have an agent represented by the blue triangle, and we would like to learn a control policy pi(e) that gets the agent to the top of the map. To do this, we give the agent a reward if it reaches the goal, and we use reinforcement learning to find a policy that maximizes collected reward. This type of setup, where most of the states yield no reward, is known as a sparse reward setting. Now, what usually happens when we train with sparse rewards is that the agent doesn't find the goal with random exploration, and training fails. One solution is to place more extrinsic rewards and create a dense learning signal that the agent can then easily follow to find the goal. While that's very feasible in this toy example, defining dense rewards for more complex tasks is difficult and requires a lot of manual tuning. So what we know is that typical RL algorithms perform well when a dense reward is available, and they tend to fail on sparse reward tasks. One idea to improve performance in sparse reward settings is to generate intrinsic rewards, which incentivize the agent to be curious and explore new states. At the start of training, when every state is new, intrinsic rewards are spread out across the map and provide a dense learning signal. While collecting these intrinsic rewards, the agent can find the extrinsic reward at the goal and solve the task. Intrinsic rewards have been shown to be very helpful when solving sparse reward tasks, like the Atari game Montezuma's Revenge. The issue with intrinsic rewards is that they're not always aligned with the goal. In this new scenario, the extrinsic rewards are close to the starting location and easy to find. But because the agent is curious, it can get distracted by the intrinsic rewards and follow them the wrong way. In this setting, it would be much better to train without intrinsic rewards and have the agent learn without any distractions. What this tells us is that intrinsic rewards can actually hurt performance in dense reward tasks. This unpredictability is an issue that prevents practitioners from using intrinsic rewards on a wide variety of new tasks. To address this problem, we propose a method that enables RL agents trained using intrinsic rewards to perform well on both sparse and dense reward tasks. Our method achieves this by using intrinsic rewards only when they help performance. We train two policies. The blue triangle represents a policy trained with only extrinsic rewards, and the pink triangle represents a policy trained with added intrinsic rewards. We propose using the following constraint. In order to train with intrinsic rewards, the mixed policy must collect more extrinsic reward than the extrinsic only policy. This is the main idea behind our method, which we call extrinsic-intrinsic policy optimization, or IPO for short. We train a policy that maximizes both rewards, subject to the constraint that intrinsic rewards should only be used if they help the agent achieve higher extrinsic rewards. IPO balances extrinsic and intrinsic rewards for us and allows us to use intrinsic rewards on any new task. To validate performance, we compare IPO with baselines using average probability of improvement across all 61 Atari games. We use PPO as our base RL algorithm, and we use a state-of-the-art method called R&D to generate intrinsic rewards. We compare three settings: PPO trained using only extrinsic rewards, PPO trained with both extrinsic and intrinsic rewards, and finally, PPO trained using IPO to balance rewards. First, we see that PPO with R&D only has a 50% probability of improvement over PPO, which suggests that PPO with R&D is not necessarily better than PPO on average. In contrast, IPO achieves a significantly higher probability of improvement than both PPO and PPO with R&D. This indicates that our method outperforms both baselines in a majority of Atari games. So thanks for listening, and please take a look at our poster for more details.